Hi, I'm Kurt, and welcome again to Comp Sci 5. Ah! Oh my gosh. Whew. Man, sorry about that. There's just so much knowledge on this board that it's so heavy. Oh my goodness. Last time we talked about big O notation and what that means in terms of growth rates for specific functions. We went over a few rules. We went over chaining components. We went over cutting coefficients. We went over dropping the lower ordered terms. And we're going to use those ideas to solve problems in terms of program analysis. We want to be able to apply big O notation to analyzing our programs in order to make them run faster and more efficient. So we're going to go right over our rules for program analysis right at the beginning because you need these rules whenever you're analyzing your code snippets. Among them are assignment statements. So like A equals B, that is an assignment statement. That takes constant time. Like a break and a block, or a continue, or a return statement for a function. Those all take constant time as well. One thing to point out, math is actually a constant time operation in the world of computers because computers do math. It happens almost immediately, and therefore we don't factor it into runtime at all. Some operations that you must be familiar with: addition, subtraction, multiplication, division, and modulo. So that's constant time. Now let's see what's different. What about other time operations? What are the variable times? And there are three major things to concern yourself with. We have loops. The rule for a loop is you need to multiply the big O of the body times the amount of times the loop runs, right? Big O of body times number of times the loop executes or runs. Conditionals, you want to take the maximum of the if-else string. So if you have an if block runs in big O n squared time and an else block running in big O n time, then the whole conditional runs in big O n squared because n squared is bigger than n. Last thing, a subroutine. Let's say you have a function calling another function in your program. Completely cool. The only thing is you need to evaluate those subroutines separately and then add them to the total result of the program. Then we'll utilize dropping the lower order terms rule of big O notation to come up with a big O expression to describe the entire function. So up on here I have a little bit of code pre-written. Let's think of them separately at first, then we'll combine them and get a greater depth of understanding because of it. So this first one right here, this is all that exists right now. Right here. We have sum equals 0. Well, that's going to be big O of 1 because constant time, assignment statement. We're in a loop now, so we're going to apply our loop rule. Let's look at the body first, see what the big O of the body is doing. Plus equals n, that's math, constant time, big O of 1. Now let's see how much time is the loop running. Well, starts at I, increments 1 every time, and goes to n. This is a big O of n times. So this whole little program would be big O of n. Let's take a look at the second one now to really hammer home this loop rule. We're going to start with the body. So the body of the inner loop is here, sum plus equals n. Similar to that, it's going to be constant time. Next, we're going to go see how many times does the inner loop run. Well, the inner loop runs n times, of course. So now we look at our rule. Remember, multiply big O of body times number of times the loop runs. Well, for the outer loop, this whole thing is the body. So we're going to multiply big O of n times big O of n, giving us a total of big O of n squared. Now we're going to take a look at what is the conditional. So I'm going to introduce a little if statement. No big deal. So we have a little if. We'll just say if, condition, con, run this snippet of code, else, if this con is not true, we're going to run this snippet of code. Well, our rule is we take the max of the if-else. So this branch of the if statement runs in big O of n. This branch of the if statement runs in big O of n squared. Therefore, using this rule, we'll take the maximum big O of n squared. Similar to a subroutine, if this was a function in your program and it called this function, then we would have two functions. We'd have big O of n squared plus big O of n, plus, a constant. And because we drop all the lower ordered terms when we concern ourselves with big O notation, we drop it, the entire program would be big O of n squared again. Thank you. That's all the time that we have today. Thank you for streaming in. We really, really appreciate your viewership. And yeah, that was Comp Sci in 5.